Swayam Prabha. Digital India. Educated India.
Good morning. This is our penultimate lecture on composite surfaces. Lecture number 39. Here I am going to be talking about how different patches can be combined together along common curve boundaries. To exemplify this, I'll consider only two cases, those of Ferguson patches and Bezier patches. Using the concepts discussed in this lecture, you can later on extend the techniques for B-spline surface patches or for other surface patch models. Composite surfaces. This is what the idea is. We need to stitch two patches together at their common boundaries. What does that mean? It means that we need to maintain position, which is C0, slope, which is C1, and or curvature, which is C2, continuity at the boundary curves. Position continuity implies when the boundary curves of two adjoining patches coincide exactly. This would mean physically the slope along the boundary curves is also continuous. We also need to ensure a unique normal at any point on the common boundary between two patches. We can accomplish this by coinciding the tangent planes of the two adjacent patches. As I mentioned, the first model is of the Ferguson's surface patch, and this is called the F-mill method, what we are going to be discussing now. Well, position or C0 continuity is ensured across patch boundaries. So we have the two parametric directions here, u and v. This is the first patch. These are the tangents along u and v. The tangents along u and v at this corner point. Likewise, tangents along u and v at this point, and the same for this point. Let's name these tangents. This tangent here is S sub I j. This here is T sub I j. This here is S I j plus 1. This direction here is T I j plus 1. This one here is S I plus 1 j plus 1. This is T I plus 1 j plus 1. This one here is S I plus 1 j, and this direction is T I plus 1 j. As you would notice, the tangents along the u direction are represented by S, and those along the v direction are represented by T. Index I is getting incremented along the u direction, and index j gets incremented along the v direction. Let's have another patch adjacent to this patch here along the u direction. Likewise, let's have a patch adjacent to this one here along the v direction. Let's say this is patch 1, this is patch 2, and this is patch 3. This point here is Pij, this here is Pi plus 1j, this here is Pi plus 2j, this corner point is Pi j plus 1, this one is Pi plus 1 j plus 1, Pi plus 2 j plus 1, Pi j plus 2, and this point here is Pi plus 1 j plus 2. What is this curve here? And what is this curve here? These are common boundaries. This one is common between patch 1 and 2, and this curve here is common between patch 1 and 3. Since all three patches are Ferguson's bicubic patches, each of these bounding curves are cubic, and so the common boundaries are also cubic curves. And so happens that Ferguson's models innately give us slope continuity along the curves. As you move along this boundary curve, the slope is continuous between 1 and 2, and as you move along this common curve here, the slope is unique along the u direction between patch 1 and 3. What do we need to then worry about? We need to worry about the continuity in the cross boundary tangents. In other words, if I stand at any point here, I would be able to compute a unique normal, which would represent the normal for patch 1 and 2. Likewise, the same here. If I stand here, I should be able to compute a unique normal, which is representative of patch 1 and 3. The same diagram here. Let's say we would want to avoid specifying higher order information. Let's work with a given set of data points Pij, where index I goes from 0 to m and index j goes from 0 to n. So in a sense, all we know are these points. Let's see where this takes us. So these are the points that we know, and let's assume that we do not know anything else. The problem is that we require to fit a composite Ferguson surface over these points. Since we don't specify these slopes as our design choices, we need to estimate them. So the intermediate slopes Sij along u and Tij along the parameter direction v can be estimated as Sij equals C sub I times p I plus 1j minus p I minus 1j over the absolute value of p I plus 1j minus p I minus 1j. Note that these points are position vectors. They are ordered sets. They contain information pertaining to all the three Cartesian coordinates. Ci is equal to minimum of the absolute values between Pij and Pi minus 1j, and Pi plus 1j minus Pij. So physically, what's happening? Let's see. Pi plus 1j is this point. Pi minus 1j would be a point here somewhere. So Pi plus 1j minus Pi minus 1j over its absolute value will be some unit vector. And Ci would be the minimum of two absolute values, Pij minus Pi minus 1j, which is this, minus some fictitious point here, Pi minus 1j, and Pi plus 1j, which is this point, minus Pij, which is this point. So in a sense, we are considering three consecutive points along parameter direction u to compute intermediate slope Sij. Let me get back, not to compute but to estimate. Likewise, the slope Tij can be given as d sub I times Pi j plus 1 minus Pi j minus 1 over the absolute value of the numerator. So this here is a unit vector. Di is minimum of these two distances, Pij minus Pi j minus 1, this minus some point here, Pij minus 1, Pi j plus 1, which is this point, minus Pij, which is this point. To compute or to estimate Tij, we are considering three consecutive data points along the parameter v direction, like these. It would be easier for you to understand if we look at the estimation of Ti j plus 1. There it will be clear that we are considering Pij, Pij plus 1 and Pij plus 2. So much so for the slope information. If patches 1, 2 and 3 happen to be Ferguson patches, recall from our previous lectures that we would need the slopes along the u direction, those along the v direction, and also the twist vectors or the mixed derivatives of r at these points. For now, we can assume that these twist vectors are 0. So a geometric matrix for a Ferguson's patch will then look like G equals the corner points in the top left 2 by 2 region, Pij, Pi j plus 1, Pi plus 1j, Pi plus 1, j plus 1. Here we'll have slopes pertaining to the v direction, Tij, Ti j plus 1, Ti plus 1 j, and ti plus 1 j plus 1. In the lower left region, we'll have slopes along the u direction in the same order: Sij, Sij plus 1, Si plus 1j, and Si plus 1 j plus 1. This region pertains to the information on twist vectors. For now, we have assumed them to be 0. So this geometric matrix G would correspond to the first patch. Now we have a slight problem. For I equals 0 or I equals m, the points p minus 1j and p n plus 1j are not known. To counter this, the user now will have to specify the slopes S0j and Smj for all values of j from 0 to n. That is, if you look at this figure, if I move along j, which is along the v direction here, for j equals 0, which would be somewhere here, let's say, we'll have to specify S0j's. And for j equals m, somewhere here, we'll have to specify Smj. Likewise, slopes t sub I 0 and t sub I n for I going from 0 to m will also need to be specified. In summary, slopes along the u and v parametric directions are to be specified on the boundaries of the composite surface. Now this model works well for evenly spaced data points, but local flatness or bulging due to 0 twist vectors, which are these here, happens to be a problem. Let's now look at composite Ferguson surface with non-zero twist vectors. So we are working with the same figure here. We can avoid local flatness or bulging by computing the twist vectors as opposed to assuming them to be 0. Well, to do so, we can impose the C2 continuity condition at patch boundaries. Now you have seen this compact form of Ferguson's cubic patch before. R super 1, which is the equation for this patch in terms of u and v, is equal to the row matrix U times the Ferguson's coefficient matrix, the geometric matrix, the transpose of M, the transpose of V. U and V contain 1 linear, quadratic, and cubic terms in parameters U and V respectively. The geometric matrix G super 1 for this patch, as you know, is Pij plus 1, Pi plus 1j, Pi plus 1, j plus 1. The slopes along the v direction, Tij, Ti, j plus 1, Ti plus 1j, Ti plus 1, j plus 1. The slopes along the u direction in the same order. And now the non-zero twist vectors represented by chi. So we have chi ij, chi I j plus 1, which is here, chi I plus 1j, which is at this point here, and the twist vector I plus 1, j plus 1 at this point. Okay. To impose C2 continuity condition, we are saying that the second derivative of this patch with respect to u evaluated at u equals 1 for all v, which is here. So if you recall, the parameter u goes from 0 to 1 here, and v goes from 0 to 1 here. So for this common boundary, u equals 1 and v is any value between 0 and 1. This should be equal to the second derivative of this patch, r super 2, with respect to u. And for this patch, for this bounding curve, u equals 0. Well, we have the expression right here. For patch 1, we use the geometric matrix G1. For patch 2, we use G super 2. Let me skip all the math and give you a set of final results. Second derivative of r with respect to u. This would involve differentiating this row vector twice. We'll get 6, 2, 0, 0 times m g super 1 m transpose v transpose. And of course, this is evaluated at u equals 1. The second derivative of row vector u with respect to u evaluated at u equals 0 will give 0, 2, 0, 0 times m g super 2, the geometric matrix for this patch, times m transpose times v transpose. We can post multiply m with this to get 6 minus 6 to 4 times g super 1 m transpose v transpose is equal to minus 6, 6 minus 4 minus 2 times g super 2 m transpose v transpose. To get 6 minus 6 to 4 times g super 1 for this matrix equals minus 6, 6 minus 4 minus 2 times g super 2, the geometric matrix for this patch. Now solve this previous expression. Let me repeat. 6 minus 6 to 4 times g super 1 equals minus 6, 6 minus 4 minus 2 times g super 2. To get this equation in terms of the slopes along the u direction, Sij plus 4 times Si plus 1j plus Si plus 2j equals 3 times P I plus 2j minus Pij. Now if you notice, a very similar equation was encountered when discussing composite Ferguson curves with C2 continuity. We will have another equation coming out from this relation, and that would be in terms of the twist vectors chi ij plus 4 chi I plus 1j plus chi I plus 2j equals 3 t I plus 2j minus tij. The right hand side corresponds to the slopes along the v direction. Let us name these equations A and B. And these equations are for index I going from 0 to m minus 2 for a fixed index j. Likewise, if we compute the second derivative for patch 1 with respect to v and evaluate it for any u and v equals 1 using C2 continuity condition, we'll have to equate it with the second derivative of the third patch, which is placed over R1, as you know from the figure. Second derivative of R3 with respect to v for any value of u and v equals 0. We can do the math. We have u m g1 m transpose 6200 transpose. How do we get this? We need to differentiate now the column vector v or capital V with respect to this parameter v and evaluate that at v equals 1. Likewise, we do the same for v equals 0 to get 0, 2, 0, 0 here. So this expression here will be u m g3 m transpose 0, 2, 0, 0 transpose. Let us skip the algebra and get to the final result. The geometric matrix for the first patch times 6 minus 6 to 4 transpose is equal to the geometric matrix for the third patch times minus 6, 6 minus 4 minus 2 transpose. If we simplify, we get another set of equations. Now, in terms of tangents along the v direction, Tij plus 4 Tij plus 1 plus Tij plus 2 equals 3 times Pij plus 2 minus Pij. And this one here in terms of the twist vectors, chi ij plus 4 chi ij plus 1 plus chi ij plus 2 equals 3 times Si j plus 2 minus Sij. Now, these equations are for index j going from 0 to n minus 2 for a fixed index I. Let's name them equations C and D. In summary, we have equation A, equation B for varying index I for fixed j, and then we have equation C, equation D for varying j and fixed I. Okay, So for given information, which is in terms of data points p I j, I going from 0 to m and j going from 0 to n, with boundary slopes S0j, Smj for all j going from 0 to n, and Ti0, Tin for all I from 0 to m, and twist vectors chi 0j, chi mj for all j from 0 to n, and chi I0 up till chi in for all I from 0 to m. And this is getting a little complicated. One needs to solve for Sij with equation A from the previous slide, Tij with equation C from that slide, and chi ij using equations B and D for I equals 1 up till m minus 1 and j equals 1 up till n minus 1. So for a composite Ferguson's patch with non-zero twist vectors, we'll summarize again. We will need data points Pij. We will need boundary slopes S0j and Smj for all j's. We'll also need the slopes along the v direction Ti0 and Tin for all i's from 0 to m, and also we'll need the twist vectors at the boundaries chi 0j, chi mj for all j's, and chi I0, chi in for all i's. Once we have this input, we would be able to solve for all the intermediate slopes along the u direction, along the v direction, and all the intermediate twist vectors. You'll need to spend some time all by yourself to understand this. A little note: equations A, B, C, and D are all tri-diagonal systems that can be solved easily and efficiently using Thomas's algorithm. Let's now come to the second model, composite Bezier surface. But before that, let's establish equivalence between bicubic Fergusons and Bezier patches. So this is the Ferguson's patch here. R as function of u and v equals u, m sub f, the Ferguson's coefficient matrix, g sub f, the Ferguson's geometric matrix, m f transpose v transpose is equal to u mb, this is the Bezier coefficient matrix, gb, the Bezier geometric matrix, mb transpose v transpose. So if we let go of the row vector here, u, and if we also let go of v transpose here, we will see that mf gf mf transpose is equal to mb gb mb transpose. So this part here is equal to this part here. Now, given information pertaining to a Bezier matrix, we can get the corresponding geometric matrix for Ferguson patch as MF inverse MB GB MF inverse MB transpose. Post multiply this relation by MF transpose the inverse and pre-multiply the same by MF inverse. Likewise, if we are given a Ferguson's patch, we can determine the corresponding geometric matrix for Bezier patch. Let's revisit the bicubic Bezier patch with control points or design points R00, R10, R20, R30, R01, R11, R21, R31, R02, R12, R22, R32, and R03, R13, R23, and R33. So, in terms of the design points that we have seen pertaining to G sub B, we can get the geometric matrix for the corresponding bicubic Ferguson's patch. The first row is R00, R03, 3 times R01 minus R00, 3 times R03 minus R02. Second row, R30, R33, 3 times R31 minus R30, 3 times R33 minus R32. 3 times R10 minus R00, 3 times R13 minus R03. 9 times R00 minus R10 minus R01 plus R11. 9 times R02 minus R12 minus R03 plus R13. And the final row is 3 R30 minus R20, 3 R33 minus R23, 9 R20 minus R30 minus R31 plus R21, 9 R22 minus R32 minus R23 plus R33. So, in a sense, gradients and twist vectors. This region here, as you know, pertains to the slope along the v direction, the slopes along the u direction, and of course the twist vectors here. So, the gradients and twist vectors at patch corners, 4 of them, can all be expressed in terms of the characteristic Bezier polyhedron. That gives us one important hint as a designer. We may, after all, not need to specify higher order information. In fact, we don't need to go through unnecessary and intricate computations that we had seen in case of composite Ferguson patches. Let's continue with composite Bezier surfaces. So, this here is the first patch. The corner point is R sub 00 of patch 1, R sub 03 of the first patch, R sub 30 of patch 1, and if we need to maintain position continuity here, the point here will also be the 0th point of the second patch. Likewise, this point here pertains to R33 of the first patch, this one, which is the same as R03 of the second patch, which is this one. As I said before, these 2 points are the same to maintain position continuity at these 2 junction points. We'll talk about this common boundary in a while. For the second patch, this corner point here is R30, and this point here is R sub 33. Patch 1, patch 2. This corresponds to the U direction. This one here corresponds to the V direction. From what we know from before on bicubic Bezier surface patches, the first patch, R super 1 in U and V, can be written as U M sub B GB super 1 MB transpose V transpose. And likewise, the second patch, R2 UV, can be given by U MB GB super 2 MB transpose V transpose. Now let's look at positional continuity. For that, across the common boundary, R1 for U equals 1 and any V should be equal to R2 for U equals 0 and any V. This would mean that a row vector 1, 1, 1, 1 times M sub B, the Bezier coefficient matrix, times the geometric matrix for the first patch should be equal to 0, 0, 0, 1 times M sub B times the geometric matrix for the second patch. Let me flash this relation for you here. GB super 1 is this matrix here, and GB super 2 is this matrix here. Now this row vector times M sub B is equal to 0, 0, 0, 1 times GB super 1, which is this, and this is equal to R30, R31, R32 and R33 for the first patch, the transpose of that. And this row vector times M sub B equals 1, 0, 0, 0 times the geometric matrix for the second patch given by this matrix here, which is equal to R00, R01, R02 and R03 of the second patch, the transpose. We can summarize these results and say that R3J for the first patch equals R0J for the second patch, for values of J going from 0 to 3. Physically, that would mean that the boundary polygon must be common between the two patches. Here is a figure. This is the control net for the first bicubic Bezier patch, and this here is the control net for the second Bezier patch. Patch 1, patch 2. All the condition that we had seen in the previous slide says that the boundary polygon between these two nets should be the same. This here is a polyline. Let's move forward and address gradient continuity across the patch boundary. For gradient continuity, the tangent plane of patch 1 at u equals 1 must coincide with the tangent plane of the second patch at u equals 0 for all values of v in between 0 and 1. So let's compute the tangent along the u direction for the second patch at u equals 0 and the tangent of the second patch along the v direction again at u equals 0. And let's compute the cross product between these two tangents. So the left hand side here will represent the normal to the tangent plane. Likewise, this expression here corresponds to the tangent along the u direction for the first patch at u equals 1. This term here is the tangent for r super 1 along the v direction for u equals 1. So this cross product here is again a normal to this tangent plane. For the two tangent planes to coincide, these normals must be scalar multiples of each other, and that is for different values of v in between 0 and 1. And because of that, we introduce a scalar lambda, which is a function of v. So what we are saying is the directions of the two normals should be the same, but the magnitudes may differ. Positional continuity further ensures that the slope along the v direction for the second patch at u equals 0 is the same as the slope along the v direction for the first patch at u equals 1. So we have two possible solutions. This equation is equation A. Case 1. The first derivative of the second patch with respect to u at u equals 0 is equal to lambda of v times the first derivative of patch 1 with respect to u for u equals 1. And case 2, the first derivative of the second patch with respect to u at u equals 0 is a linear combination of the first derivative of patch 1 with respect to u and the first derivative of patch 1 with respect to v. The two scalars we use are lambda of v and mu of v. If you plug in this equation here, you will see that you get the right hand side. Of course, case 2 is a generalization of case 1. Let's look at case 1 in detail. Okay. Partial r2 over partial u at u equals 0 and v equals lambda of v times partial r1 over partial u at u equals 1 and v. This implies 0, 0, 1, 0, m sub b, g sub b of the second patch, geometric matrix, times the Bezier coefficient matrix transpose, v transpose equals lambda of v times this row vector here with elements 3, 2, 1, 0, M sub B GB1 MB transpose V transpose. Now, if you notice, the left hand side is cubic in V. V transpose here comprises of terms 1 V, V squared and V cube. For this equation to hold good, the right hand side should also be cubic in parameter V. We already have cubic terms in V transpose here. For that to happen, lambda of V should not be a varying function, but should be a scalar constant, lambda. We can equate coefficients of V to get 0, 0, 1, 0, M sub B GB of the second patch, MB transpose equals lambda 3 to 1, 0, M sub B GB of the first patch, MB transpose, and if we further post multiply this equation by MB minus transpose, we get 0, 0, 1, 0, MB GB2 equals lambda times 3, 2, 1, 0 times MB GB1, which converts to R1I of the second patch minus R0I of the second patch equals lambda times R3I of the first patch minus R2I of the first patch, where index I goes from 0 to 3. This is the condition from the previous slide. Geometrically, what this condition means is that the 4 pairs of polyhedron edges meeting at the boundary must be collinear. So this is the first bicubic patch. This is the second Bezier bicubic patch. These 4 lines must be collinear. From position continuity, we had already seen that this was a common polyline between these 2 patches. So if you notice, from the design viewpoint, these 8 points are constrained. These 4 points get constrained because of position continuity, and these 4 points get constrained to lie along these respective lines to maintain a unique tangent plane at this common boundary. In other words, these are not, so to speak, free choices anymore for us. Let's look at case 2 now. Partial of R of the second patch with respect to U at U equals 0, V equals lambda of V times partial of the first patch with respect to U at U equals 1 for any V plus any scalar as a function of V times partial of R1 with respect to V at U equals 1 and for any V. Mu of V is another scalar function of V. This condition gives us 0, 0, 1, 0, MB GB of the second patch, MB transpose V transpose equals lambda v 3, 2, 1, 0, MB, the geometric Bezier matrix for the first patch, MB transpose V transpose plus mu of V 1, 1, 1, 1, MB GB of the first patch, MB transpose times this column vector here, 3V squared, 2V, 1 and 0, pertaining to partial over partial V of V transpose. In this expression, we must match the degree in V, which would mean that the scalar lambda is no longer a function of parameter V, it's a constant, but we can have mu of V as a linear function in parameter V. Mu 0 and mu 1 are scalars, constant scalars. If we work out this condition and we try to figure what that condition means geometrically, this is the first patch, this is the second patch, the condition gives a more relaxed situation here in terms of how a user can specify data points freely. The second case states that these three edges must be coplanar. Likewise, these three edges also need to be coplanar. So what do we have? We have a common polyline here that gives us position continuity between these two patches. And then we have this point to be specified such that these 4 points lie on the same plane. And likewise, for this patch, we have to specify this design point such that 1, 2, 3, and the fourth point lie again on the same plane. These two planes can be different. In this lecture, I have covered quite a bit of material on composite, Ferguson, and Bezier surface patches. I would suggest that when you're watching this video, you go through each and every step slowly and try to work out the equations all by yourself on a piece of paper. Although I have considered only Ferguson and Bezier models, similar concepts can be used, can be extended to B-spline surface patches and composite B-spline surfaces. This is only to give you an idea as to how composite surface patches or composite surfaces get modeled in CAD.